Hypothesis testing is a method for making decisions with data when randomness is unavoidable. In the real world, we almost never see an entire population. We see a sample, and samples naturally vary. The problem hypothesis testing solves is simple to state and hard to answer. Did we observe a real effect, or did random variation just happen to look meaningful this time? The key idea is surprise under an assumption. We temporarily assume a baseline claim about the world is true, and then we ask how surprising our data would be if that claim really held. If the data would be very unusual under that assumption, we treat the data as evidence against it. Hypothesis testing does not prove things are true. It measures incompatibility between data and a claim. That baseline claim is called the null hypothesis, written H0. It represents the status quo and always includes equality, like the population mean equals 250, or the difference between two groups equals 0. The competing claim is the alternative hypothesis, written H1 or HA. It describes the kind of effect we are looking for, such as not equal, greater than, or less than. We never prove the alternative. We either reject the null or fail to reject it. Before seeing any data, we must decide whether the test is two-sided or one-sided. A two-sided test asks whether the parameter differs in either direction. A one-sided test asks whether it differs in one specific direction only. This choice must be made in advance. Choosing the direction after seeing the data makes false positives more likely. So how do we judge surprise? We rely on sampling distributions. Even when the null hypothesis is true, sample statistics, like means and proportions, vary in predictable ways. For many common problems, we know the distribution of a standardized statistic if the null is true. That allows us to compute probabilities. A test statistic turns raw data into a single signal. Most test statistics have the same structure: observed value minus the value predicted by the null divided by the standard error. In symbols, it looks like observed minus expected over noise. If the statistic is close to 0, the data are consistent with the null. If it is far from 0, the data are unusual under the null. From the test statistic, we compute the p-value. The p-value is the probability, assuming the null hypothesis is true, of observing a result as extreme as or more extreme than the one we observed. Small p-values mean the data would be rare if the null were true. Large p-values mean the data are not unusual under the null. This definition matters. A p-value is not the probability the null hypothesis is true. It is not the probability the result happened by chance. It is not a measure of how big or important an effect is. And a large p-value does not prove there is no effect. It only says the data do not strongly contradict the null. To make a decision, we choose a significance level called alpha before analyzing the data. Common choices are 0.05 or 0.01. Alpha is the long-run rate of false positives we are willing to tolerate. The rule is simple. If the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we fail to reject the null. Because decisions are made from samples, errors are possible. A type 1 error is rejecting a true null hypothesis. Its probability is alpha. A type 2 error is failing to reject a false null. The probability of avoiding a type 2 error is called power. Power increases with larger sample sizes, larger true effects, and less variability. Consider a concrete example. A company claims cereal boxes have a mean weight of 250 grams. We test H0, the mean equals 250, versus H1, the mean is not 250. From a sample of 25 boxes, we get a mean of 246 and a sample standard deviation of 10. The t-statistic is -2. The corresponding two-sided p-value is about 0.056. At alpha equals 0.05, we fail to reject the null. The correct interpretation is that the data are not strong enough to conclude the mean differs from 250 grams at the 5% level. The incorrect interpretation is that we proved the mean is 250. This example shows why sample size matters. With the same difference but a larger sample, the standard error would shrink, the test statistic would grow in magnitude, and the p-value could drop below 0.05. This is why hypothesis testing should not stand alone. Effect sizes tell us how big the effect is. Confidence intervals show a range of plausible values and the uncertainty in our estimate. A result can be statistically significant, but practically trivial, or not significant, yet still consistent with meaningful effects. In practice, hypothesis testing follows a clear workflow. State the research question, define the null and alternative hypotheses before seeing the data, choose alpha, select a test appropriate for the data and design, check assumptions, compute the test statistic and p-value, report the decision along with effect sizes and confidence intervals, interpret the result in context. The core takeaway is this. Hypothesis testing asks how surprising your data would be if a baseline claim about the population were baseline true. It is a tool for disciplined decision-making under uncertainty, not a machine for discovering absolute truth.